record the, okay, I'm recording this now, so you'll get a verbal recording as well as the visual recording. So
the map is well defined is only when these two elements are
these
true.
two conditions are true, right? The
Okay.
first condition is for every domain element A, for every element A that's in the domain capital A, there has to exist, that's the backwards E, an element B that's a member of the codomain such that the image of A is B. So for each one of these domain elements has to have a codomain partner. If there was one that in the domain that didn't have a partner, it's not a map. That's condition one. Condition two is, which sort of assumes condition one
Thank you,
is,
Fernando. Hold on, my dad can't hear you.
okay, there. Okay, so for every that this one deals with sort of this second condition is the no one to many pairings. And that one says if you take any two arbitrary elements of A, then you can look at it two ways. Either if the image of A1 is not equal to the image of A2, then those can't be equal. On the other hand, if they are equal, then the images have to be equal. It forbids either case. It forbids it in one of two ways. It's for two ways of looking at this. You start, these are different. These ones have to be different. You have to have this, but you can't have this. If these are the same, you can't have them split up. In either case, this is the situation there. Okay. Then we looked at, go ahead,
I have a
Will.
question about this. So, does that mean this is like when our matrices have, or sorry, our linear expressions have the same elements and are essentially the same line, but we can't just delete them? This handles that
No, this has
situation.
nothing to do with this.
Oh,
This is something completely new. We haven't seen, so that you shouldn't try to, you're trying to sort of interpret some of our earlier ideas, but the earlier ideas always deal with one vector space.
okay,
This is going
got
to
it.
deal with the relation. Our linear maps are going to be between two vector spaces. So these aren't vector spaces yet because but what they will be. So think of A as one vector space, B as a second vector space.
Yep. Okay.
So they're not, so that you're going to have a basis for A and a basis for B, and there'll be relations between the vectors in A, and those are separate. Oh, they might be connected by the maps, but that's a question for investigation. So all the concepts we've had before apply either to A or to B,
Yep, but not okay, got
but
it.
they're not. Yeah, so don't put the two together. Okay. The second thing was we had two properties, onto and one-to-one, and if you put them together, you have a correspondence, right? Sort of both. Okay, what does onto mean? It means for every B member of the codomain, there is an A member of A such that F of A equals B. What this one says is for every codomain element, so it's onto, if this map here is not onto because there's a little dot here that isn't paired. It says for every element B, there's got to be a pre-image A that maps to it. So for every image, every element of B must be the image of some element in A. It's sort of the opposite of this. This one starts off for every A, it's got to have an image. The ontoness says for every element in B, it's got to have a pre-image. So this is not a condition to be well defined. It's a just a property of maps. Okay, Will, question.
So the first explanation was just going over a one-to-one map, or was that
We
just
haven't talked
all
about
linear
this. We
maps?
haven't talked,
Okay, got it.
and this is not
Yep.
linear maps. We're just talking about maps. This is just being a well-defined map.
Oh, okay,
This
got
is
it.
just, there's two conditions to be a well-defined map. Then there's two properties.
Okay. Okay.
But the two properties are sort of the opposites of the two conditions for the well-definedness of a map. See, this is sort of saying the map allows codomain elements not to have partners, but the ontoness condition says, no, that can't occur. Every codomain element has to have a partner. Okay? Now, the one-to-one map says, is sort of the opposite of this one. It says if for every element A1, for every two elements A1 and A2, if if A1 is not equal to A2, then F of A1 is not equal to F of A2. So you look over here, it's this one says is the opposite order, right? It's got the images imply the pre-images. This one's the opposite. This one says if A1 is not equal to A2, right? If they're different, then F of A1 is not equal to F of A2. What it's doing is it's saying if these two are separate, then the images are separate. And notice what it forbids is 2 going to 1, right? It forbids many to 1. So to be a map, you can't have 1 to many, but to be 1 to 1, you also can't have many to 1. So in some sense, these two properties are the reverses, are the opposites in some, or they're sort of like they take it the other way around, right? So it turns out that you notice if you had both of these properties, that would be okay. That would be the conditions for defining a map from B back to A. And that's what's going to happen is that if I want to have what's called an inverse map, then I'm going to need to have both ontoness and one-to-one properties. So there's these two properties here. And again, there's a sort of there's the negation view, and then there's the sort of the contrapositive, which is the more positive view, which says if F of A1 equals F of A2, that implies that A1 equals A2. In other words, if two things are the same, you can't have this. It will turn out that A1 has to equal A2. Again, if you have one element here, they can only come from one. You can't have many to one. Okay, these are the formal definitions of what we did intuitively last time. Are you guys okay with this?
I am. I'm not sure about my peers.
Okay. Well, the way you'd use these would be, I think, in proofs, right? In other words, the formal the first thing to do is to understand them intuitively, and then this sort of gives you at least the idea that these are very precise definitions. And what we're going to do is they provide the basis for how, when we come to linear maps, how to verify that a map between vector spaces is onto and one-to-one. And we'll go and do that concretely, hopefully at towards the end of this class. So, well, now we need to come to the main topic here, which is linear maps. So a linear map is a map, say M, between vector spaces V to W. So you have a vector space V, a vector space W. So the domain, say, is V, and the codomain is W. And it satisfies the same, it's well defined if every vector in V has an image in W, and if no, one of these vectors can't go to 2 over here. Now let's look at an example. Let's say we have M from R3C to R2C given by the following So we take any vector in R3C. So that's like, so this has, we can choose any values we want for X, Y, and Z, and that's mapped to, here's a second notation for this, that's mapped to by M, say X plus Y and X plus Z, okay? So for every element, for every element in every vector in the domain, we have an element in the codomain. So that satisfies the first property, and it also satisfies the second because I can't. I mean, it directly depends on these things. Like if this was different, right? If I had two of these and they were different, that would imply I could go through and check that this satisfies both of those conditions for being well defined. And this one happens to be. I think the question is it one-to-one and onto? Well, it's not. Let's say that it's not necessarily, um, um, let's see if we can see, um, well, we have to check, is this one-to-one or onto? That would be one question, is to check whether this was having those problems. But let's just go through and see this, because this doesn't illustrate, this is just a map, right? And we can ask, is it one-to-one or onto? Onto, one-to-one. But what about this word linear? Okay, well, a linear map is a map between vector spaces that, in some sense, preserves structure. Well, what we mean by that is linearity, linearity. So it works nicely with linearity. Now, what that's going to mean is this, that a map is linear if it has the following two conditions. If f of v, this is sort of the two conditions for being linear. F of v1 plus v2 equals f of v1 plus f of v2. So it's sort of like, what it says is the image of a sum of vectors is the sum of the images. So that, okay, then let's say the second condition. The second condition is the image for any, this is for any vector. If it's true, this has to be true for any vectors v1 and v2. And if it's also true for any real number v and any vector v, any real number r, any vector v, that has to equal r times f of v. So that means the image of a rescaled vector is the multiple of the image, okay? So you can just sort of pull out the r. Now, let's see. Now, linearity usually deals with linear combinations. Let's see if f is linear, what happens to f of a v1 plus b v2? This is an arbitrary linear combination, right? In the domain. And well, by the first property, we can divide this up into f of a v1 plus f of b v2, right? That's the first. I can take a sum and divide it into these two. Then I can use the second property here twice, once to pull out the a and once to pull out the b, to get a f of v1 plus b f of v2. So the idea here is the map is linear. These are actually going to be equivalent. I can actually go back and forth and say, if it has these two properties, then the image of a linear combination is the same linear combination of the images. In other words, I sort of combine v1 and 2 with a and b, or I can combine their images, and the image of a linear combination is sort of the same linear combination. So this is what we mean by preserved structure, okay? And it's a very strong constraint, because it's going to turn out that linear maps have a lot of nice properties with respect to the properties of vector spaces, which you've seen in the last chapters. So, and so we want to explore that, which we need to look at some examples. Or at least let's look at an example of a linear map, say a different name, G, from say X, Y. It's gonna be X, Y to X, X. Okay, so G is a map from R to C to R to C. So it's a map. So the domain is the two component vectors. The codomain, we're going to think of it as different, even though it's the same space, because it could be actually like okay, let's just do it this way. Okay, well, let's see. Is this so if I take any vector v, right? If I take an arbitrary vector v, this is its image, right? So it's, and that, what is it well defined? Well, well defined means what we want to forbid for being well defined is that one element can't go to two different ones. So let's say we had suppose that x1, x2, well, it's actually, these are all the images, right? So we have x is not equal to x2, x2, right? That this is the images of two elements here. Well, we want to show that this implies that that the that okay. Here, let me start again just to make this a little clear. Let's look and choose which one of our conditions up here for well-definedness we want to look at. Okay, we can either look at this one or we can look at the second one. Let's look at this. Let's see the second one. Let's choose two domain vectors. V1 equals x1, y1, and V2 equals x2, y2, and see if what we want to show is, for the well-definedness condition, if these two domain vectors are the same, then their images are the same, right? So we want to show that if V1 equals V2, if that implies that G of V1 equals G of V2. This is the well-defined condition 2. Let's say well-defined condition 2. Okay, well, since I've chosen two arbitrary vectors, V1 and V2, I want to suppose, right, that suppose V1 equals V2. Well, in terms of components, that means that x1, y1 equals x2, y2. And what does that imply? Well, as vector equations, that implies that x1 equals x2 and y1 equals y2, okay? So then we want to check, does the image of V1 equal the image of V2? Well, G of V1 equals, well, G of x1, y1, which equals x1, x1. Okay, well, because x1 equals x2, that equals x2, x2. And that one equals G of x2, y2. So there, which equals G of V2. So we've shown that if you suppose this is true, this is true. Now, even though it seems sort of overly simple, you can see each one. I've given the vector quality that implied or led to the numerical equality. And then I looked at the left-hand side of this, acted with G. Here's where G enters, right? And then was able to use this numerical quality to produce the second one and show that they're equal. That means that this map is well defined. Now, what's going to happen in practice, as long as the components of this vector, no matter what vector spaces they are, as long as the components of this vector are linear combinations of these variables, the map's going to be linear. So you're going to be able to tell that a map, I mean, that's well defined. That map is well defined. Well, that shows it's well defined. What about the let's look at, is this linear? Okay, well, what we want to do is there's two ways we can do it. We can either look at this first way here or this second way here. But let's do the first way. We can do one of both. Let's look at G of V1 plus V2. Okay, well, we have to choose two arbitrary vectors, V1 and V2. Well, let's say we use these two arbitrary vectors up here. And so we'll say, well, this is equal to G of X1, Y1 plus X2, Y2. Okay, then we can use the domain operation to make this into X1 plus X2, Y1 plus Y2. That's just in the domain. But then we can act with G, right? Because G is given by this map. It tells us the image of XY is XX. So we can say this is equal to X1 plus X2, X1 plus X2. Because I've acted with G. G just takes the first component and duplicates it here. Okay, what's that equal to? Well, I can see here that this is equal to, I can divide it, sort of undo this sum here. This is equal to X1 plus X2 X2. Okay, well, this is G of X1 Y1 plus G of, see, this is X2 Y2. So therefore, G of V1 plus V2 equals G of V1 plus G of V2. So you want to look through and see what the specific, this is a property in the domain of adding vector spaces. We put it in a form where we can apply the map G. We've applied the map G. Then we undid this vector sum, which is actually in the codomain, so to speak. And then we sort of reversed it to find, oh, this is the image of X1, Y1. So we managed to show that first property is linear. And if we do the second property, Will, you have a question?
So I'm only a little confused about why the Y's are turning into X. Is that just
Oh, okay.
because
Here's, well, that's the depth.
is
See,
that the original property of
that's the map, right?
yeah,
That's the weird,
XY
see,
equals
that's the
XX?
weird property of the map is that G of X, Y equals XX.
Okay, I just wanted to be sure.
Yeah, it's like I take any, so this is a weird map, right? I mean, you can see it's not going to be onto because it's not going to have all the vectors in R2. That's why it feels weird.
Yeah, I just wanted to be sure was this specific case and not
Yes, that's why. So
the property. Got it.
there's going to be, this is going to be the image of more vectors than just this one, but it is the image of this vector. So we can verify that it's linear. And now we can go and do the second property, which is G of R V1, say, which is going to equal G of R times X1, Y1, right? Because I just put in for V1, which is equal to G of Rx1, Ry1. That's how the multiplication by scalar is defined in the domain. Then, well, I know now that I have this in a form that I can apply the map, I know that the image is just going to be Rx1, Rx1. That's the forgetful. That's what G does. But then I can pull out the R here. That's R times X1, X1, right? And I know what the image of X1, Y1 equals X1, X1. So therefore, this is equal to R times the image of X1, Y1, which equals R times G of V1. So that's the second property, 1, 2. Therefore, G is linear. Okay, well, it's pretty obvious when a map is linear, because the image and a vector have to be a linear. The components here have to be a linear combinations of the components here. So you can sort of tell by eyeballing it what's true, and then that guides you. And if you're asked to do the explicit verification, well, let's see, is this map onto?
Can we stay here for just a second, just
Sure.
so I can write everything down?
Okay, so we can check whether it's onto. You okay, Will?
Yeah.
Okay. If it's onto, well, what property do we have to have? We have to say is it's going to be onto if, let me, there. Okay, it's going to be onto if for every W, that's vector in the codomain, there exists a V member of the domain such that F, whether G, such that G, oh, sorry about that. Such that G of V equals W. Here, let me, there, okay. So for every W member of the codomain, there has to be a member of the domain such that the image of the domain vector is that chosen W. So we have for all W's, let's choose a W equal to, say, X arbitrary, okay? That's an arbitrary element of the codomain. Well, we have to find that there's one that maps to it. Well, no, that's not quite right. We have to find an XY, right? We have to find, say this is an arbitrary one. Well, that has if we have to, okay, given a W, this is our W, say, for arbitrary X and Y, then we have to find a V that maps to it. And you can see that there's not going to be one, because what we'd have to do is we'd have to say, well, we'd have to find a G of V which equals W, right? So we're looking for a V, which is, say, let's call it R and S, right? Such that G of R and S equals X arbitrary, Y arbitrary, right? We want to say, okay, I choose an arbitrary vector. The W, the codomain is R2C. This is an arbitrary vector of X and Y in this domain. We want to know, can we get to this one from some out? We have to find an R and S such that this is true? Well, we know what the image of this vector is. It's just RR, right? So we have to solve this system, XA, YA. Okay, so we have to solve the system. The image of some domain vector is equal to an arbitrary codomain vector. Well, obviously there's a problem because these are the same and these could be different. So no, it's not onto. Here's a counterexample. 1, 2 is a member of W, right? So if I take the sort of the vector form here, RR equals 1, 2, then R has to equal 1 and R equals 2. I mean, formally, this is a linear system, and I do a row operation and get 0, but we'll do that we'll do a more complicated case when this is a little bit less trivial or obvious. Okay, so we have a contradiction. G is not onto. Okay, well, that does the onto property. We're not onto. Now we can also do, we have to do check 1-to-1. Is it 1-to-1? Because it could be not onto, and it could be 1-to-1. Well, what does the 1-to-1 property mean? It means you can't have anything like many to one, right? 1-to-1 means no things like this. It will be V1 not equal to V2 going to the same W, right? So we can go back and choose which form we'd like to do of the 1-to-1 condition. Let's go back up there at the very top and see, here's 1-to-1. And it's this positive one where it says for every A1, if the images are the same, then the domain elements have to be the same. Okay, so let's choose two arbitrary V1 and V2. So we have V1 equals x1, x2, and I'll just write this v2 down, then differential x1, y1, and x2, y2. Differential, you had a question?
Yes, Professor. My question is there like same elements in the codomain? Why are we writing them as two elements? Why it's not just one element?
Oh, well, we want to forbid this from happening. We want to say that the condition is um, um, if how to say it this, if given that f of v1 equals w1 and f of v2 equals w2, if w1 equals w2, that's going to imply that v1 equals v2. I can't have two elements here. If I imagine this, imagine me picking, I reach into the codomain blindfolded and pick out two elements, W1 and W2. Now, I could, because I'm blindfolded, I could have chosen two elements the same, right? Or you choose one and I choose one. We could have chosen the same ones. If we do, and then we look at the pre-images where they come from, right? If they're such that they do have images, then if W1 equals W2, then it has to be that V1 equals V2. This is the same as F of V1 equals F of V2. Then it has to be, so I can't have this. I can't pick out two arbitrary elements here and find the same ones here. So what I have to be able to do is say if I choose arbitrary W1s and W2s, right? So I choose, say, X1, X1, and I say that's equal to, X1, X1, X2, X2. If these are equal, I want to show, can I show that they go to the same, these two are the same, right? Well, so I assume this, and I say, well, this is equal to so I know that if this is equal, what do I know for this? I know that x1 equals x2. Well, can I show that x1 y1 equals x2 y2, which is this one here? And the answer is no, I can't, because although x1 is equal to x2, I can choose y1 not equal to y2. So I have a counterexample. Let's make a counterexample. Let's suppose that, let's choose, like, let's choose two, let's say 1, 2, and let's say that's V1 and V2 is 1, 3. Okay, you have a question.
No, Professor.
Oh, okay. Okay, so we have V1 equals 1, 2, and V2 equals 1, 3. Then why did I say F? I'm keeping, sorry about that. This is G of V1 equals W1 and G of V2 equals W2. Then if G of V1 equals G of V2, right? So if I have these two vectors here, then G of V1 equals 1, 1, and G of V2 equals 1, 1, but V1 is not equal to V2. So it's a many to one map. You can see that, right? I can have, if I look at G, I can just see that I've got, here's G. I can have an X going to one vector with whatever X is, I have a vector here, but I have I can choose Y to be anything and they all go to the same one. So this map is not 1 to 1 and it's not onto. So it is not onto, not 1 to 1. Okay, so that's sort of how you would, if you're asked to verify, you're given a linear map and you're asked, is this linear? Is it 1 to 1? Is it onto? Okay, well, this gives sort of an example when they're not, and so we'd have to go through and do another example when they are. We only have 5 minutes left, so in the class. So let me go through and let's look through and see where we are in the text and maybe go a little bit beyond that to see. Okay, so here we are with linear maps, and we have correspondences. The first section is on correspondences in linear maps. So the idea here is here's a linear map that's going to be linear, right? And it's going to turn out also that it's 1 to 1 and onto. So they're first giving the idea of a correspondence. So a correspondent, the correspondence is a map between two sets, that's 1 to 1 and onto. This is reviewing that. Here's the definition of a linear map. Okay. Now, an isomorphism is a linear map that's both 1 to 1 and onto. So our first maps that we're going to look at in this first section of this chapter that we'll continue with are isomorphisms. And what an isomorphism is a linear map that is 1 to 1 and onto. So the previous map G was not an isomorphism because it was neither 1 to 1 nor onto. So let's try the map, say H, which is from X, Y to X plus Y, X minus Y. Okay, so this map is going to be linear, and I think we're going to be able to show that it's also one-to-one and onto. Now we'd have to go through like that and check all those three properties if we wanted to know for sure that that it is one-to-one and onto. Okay. Now, if it is an isomorphism, something nice is going to happen because a linear map acts nicely with the bases of both vector spaces. So we're going to be able to show that a linear map that's an isomorphism is going to map basis vectors to basis vectors. And we're going to see that the only isomorphisms that are possible are between vector spaces that have the same dimension. So I'm not going to be able to have an isomorphism between, say, R2 and R3 or R3 and R2. It's only going to be between R2 and R2 or R3 and R3 or from P2 to R3 or from R3 to P2 to vector spaces that have the same dimension. So that's going to be a nice thing because it's going to sort of say that what we mean by vector spaces being essentially the same is this is an idea. A linear map preserves structure. An isomorphism is a if two vector spaces have an isomorphism between them, or an isomorphism detects when two vector spaces are essentially the same. So this is going to go and sort of make it, if I have a row vector and a column vector, those are essentially going to turn out to be essentially the same. And you sort of expect that. I mean, a row vector and a column vector are going to behave the same way, but it also turns out that P1, the set of A plus BX, such that A and B are members of R, and this is R2R or R2C, and this is R2R, the row vectors, the column vectors. This is linear polynomials. Well, it turns out that P1 is isomorphic to RC2, which is isomorphic to R2R. And so these are all isomorphic. That means they're essentially the same because I can write down an isomorphism between the vector spaces. So it captures that intuition that even though these vector spaces are different, the polynomials are not the same thing as column or row vectors. Row vectors aren't the same kind of object as column vectors, but they behave the same way. So, and that's where we sort of have gotten to. And so this section on isomorphism just tells you it's a correspondence and it's a linear map. And then this one here is a see this map here that we went up here, apart from it is the same. So this map here that I wrote down here, although it's called F, is an isomorphism. And I go through an example 2.2, and if you look at 2.2, it's several pages, but it comes and verifies all three conditions. And here's another example of verifying those three conditions, and another example. So these are all examples of verifying that a vector space is an isomorphism, and there's special cases. Okay, well, let's stop there, and we'll continue next time with consequences of isomorphisms, and then we want to move on to the case when a map is not an isomorphism. It's either not onto and not one-to-one, and we want to have measures. We're going to define measures of how much it's not one-to-one or consequences. And it's going to turn out that every linear map can be represented by a matrix, and every matrix represents a linear map. Okay, so we're going to implement in the next chapter the action of linear maps by matrices. And that will bring in, sort of tie lots of pieces together, and we'll be able to apply it to linear systems and Gauss's method. And we'll sort of see the whole picture. We can see the whole subject from a sort of a global vantage point that sort of explains why things are working the way they are. Okay, well, let me stop there, and feel free to head off. Yeah, it should, we're sort of getting to the summit of the course, like sort of like all this linear maps are sort of the crucial thing that sort of ties everything together. Any questions? Feel free to head off. I will come back in a few minutes for
Thank you,
to
Professor.
office hours. Sure, will. Yeah, I'll be back at office hours, but then we'll have more courses, the multiple, because architecture people might come in too. And some of you are architecture people.
Professor,
Dipanshu, you have a question? I'm not
Oh.
hearing, I see you're talking.
yeah, I don't have a question.
Okay, you're,
Can you hear me?
yes.
Okay, so I don't have a question. I was just wondering if you could record the Friday's lecture. I know it's a big lecture, but I have a doctor's appointment on Friday.